The Canadian Shield is the largest single expanse of ancient rock anywhere on planet Earth. Dating back 4 billion years, these rocks are a storehouse of ancient history, a record of dramatic events in our planet's evolution. But how did the shield form? Where did its rocks come from? And what stories do they tell? Stories of money, dreams, and ingenuity. Stories of rocks from other planets. Stories of the rocks that formed deep beneath our feet and are now mysteriously exposed on the Earth's surface. A team of researchers from Newfoundland's Memorial University and the Smithsonian Institute are getting ready for a very unusual journey.
Now we got to find the cheese.
Geologist Derek Wilton is on a mission to deep time to uncover the mysteries of some of the oldest rocks on Earth. He's traveling with colleagues Paul Sylvester and Stephen Loring. Geology students complete the group. Our scientists are among the few who have set foot in the remote Torngatz Mountains.
Ah! Le fromage!
Derek hopes to take his team back to the beginning of time. In the next 7 days, they will sail 300 nautical miles up the coast of Labrador to reach the heart of the Torngatz at Rama Bay. En route, they will make a number of stops to collect samples of rock formations for analysis in the laboratory. Throughout their journey, they will be in the experienced hands of Captain Joey Agnetuk, an Inuk who deals with the day-to-day difficulties of navigating in waters that are still barely charted.
Some places you could be going along, be say 300 feet of water, and within a blink of an eye, that 300 feet could come up to 10 feet. We got the Torngatz above us, and we got the Torngatz below us.
Derek hopes to learn how old the rocks of the Torngat Mountains really are and understand the process that formed them billions of years ago. To do that, he needs to collect samples of zircon, a very special mineral that records the age of ancient rock.
So how do you know where to look?
Well, we know that the Rama group, those sediments, are collectors of these zircon. It's like, I like to think of it as like a black box like you have in an airplane that records, you know, what's happening in it, because the mountain is in that little crystal. The story of that mountain is in that little crystal.
Zircons are microscopic crystals with a layered onion-like structure. Each layer forms when the surrounding rocks are heated almost to melting point deep underground during the mountain building process. Minute amounts of uranium in each layer slowly decay to lead at a steady rate that never varies, and the lead gives the age of the mountain building. If he can find the right samples, Derek Wilton may be able to recreate how the ancient mountains in the Shield were transformed billions of years ago.
That's really a jewel of Canadian geology, this particular park and these particular sets of rocks in here. We're going to go in there and hunt for those zircons. They're just waiting for us. I can almost hear them calling, "Date me, date me." The origin of the Earth awaits us in there.
The Canadian Shield is the foundation of more than 2/3 of North America, stretching many thousands of square kilometers from the Arctic Ocean to Mexico and to Greenland. The outer extremities of its surface are buried under younger rocks, as in Arizona, where the shield lies exposed deep within the legendary Grand Canyon. The story of the shield begins shortly after the beginning of our planet, 4.5 billion years ago. At that time, the surface of the Earth slowly began to cool, allowing the first continents to crystallize as small floating rafts of granite, surrounded by an ocean of molten lava. Over the next 4 billion years, these rocky rafts migrated across the Earth's surface, clumping together to form larger continents. Trapped between colliding blocks lie the stretched and deformed remains of ancient ocean floor crust and sediments that were squeezed and thickened into giant mountain ranges once as high as the Himalayas. Our team from Memorial University has decided to take a first look at the mountain chain about 100 miles north of Nain. It's a landscape that expresses all the contradictions of the shield: beauty, strength, and danger. At last they can get their hands on the beautifully exposed rocks of the Torngat Mountains.
This chert layer has been eaten out by this very hot magma that was injected along this layer. And you can see that there are pieces of the chert that have been engulfed by this very hot magma.
Oh, yeah.
These magmas formed very early in the Earth's history when the Earth was hot enough to produce things like this.
A few hours later, Derek and his team discover a mineral deposit composed almost entirely of the iron mineral pyrite. This mineral forms today where superheated waters vent at the bottom of an ocean.
How do we have a 2 billion-year-old bottom of a marine basin exposed here in the Torngat Mountains? Well, obviously it goes back to mountain building events and stuff like this, because this was at one time the bottom of an ocean or an oceanic basin. Now it's on land, and in fact it's exposed on this high cliff right here. So it gives us graphic evidence of how the Earth is in constant motion. Wow. What a big waterfall. The land before time, hey?
Our researchers soon come across another clue indicating the former presence of an ancient ocean. A piece of beach now hardened to sandstone.
The ripples, the ripple marks in this quartzite, and so that tells us that this stuff was deposited on a beach. These sediments were produced by the wearing down of the ancient mountains that were here before.
The ancient beach is made up of fragments of older rocks. It's a testament to the existence of a former mountain range worn down by the forces of erosion. The many different rock layers of the Torngat Mountains point to many cycles of mountain building and erosion. It's a continuing process, which geologists are slowly unraveling.
You have to go in the field, you have to collect the material. And if you divorce yourself from the field, if you're not there actually collecting the samples and being part of it, you lose the essence of the material.
Derek has just discovered signs of very ancient life forms.
This particular layer of shale has thin seams of coal-like material, which is just phenomenal. So this makes this some of the oldest coal that we know on planet Earth. Ah! Fantastic. Fantastic.
For our scientists, this prehistoric coal is evidence of very primitive life on Earth, billions of years ago.
To many people, the rocks seem dead. To geologists, they are living things. They are an evolution of where we came from, fundamentally. The carbon in the rocks provide the best evidence for the ultimate question in science: where did people come from?
Archaeologist Stephen Loring is on the expedition to search for early traces of human activity. He's looking for Rama chert, hard as glass but much stronger, the raw material for making tools by early humans.
Wonderful thing about Labrador is, every time you go ashore, you think you're a pioneer, you think you're the first person in this area, and yet no sooner do you get ashore, you start to find traces of previous occupation, tent rings or food caches or old house frames, kayak rests. Some people did get up to Labrador over 10,000 years ago. A site like this, you might be able to find a few flakes.
Do you know what that looks like? Rama chert.
It's Rama chert. It is Rama chert.
Fantastic. Believe me, I know lots of rocks. There's not many rocks that you can actually see through. It almost looks like glass.
We brought with us some of the most extraordinary pieces of stoneworking in Rama chert. Large bifaces made by maritime archaic Indians maybe 4,000 years ago. Tools were only found in ritual caches or at cemetery sites in the graves. Tools were only made out of Rama chert, and that created this great value for the stone, that thousands of years ago people would travel all the way up here to northern Labrador to acquire this raw material to make their tools.
Some of these chert, it looks like it has black material in with the white, and that may actually be the remains of early life, organic material. Kind of interesting, kind of neat that Stephen and I both have this sort of fixation, if you want, on the Rama group and the Rama chert, but from different perspectives. He's looking at it from a human perspective. I'm looking at it from a geological perspective, and that's what's kind of really neat.
It's the dawn of the third day, and never before has Joey taken his boat this far north in the Torngatz. Icebergs that have drifted south from calving glaciers in Baffin Bay litter the icy waters. 50 nautical miles now separate the geologists from their ultimate goal. Derek is going to take his team deep into polar bear territory to climb one of the highest mountains of the Torngatz.
We're going to take samples at different areas up through the Rama group, trying to find the world's oldest zircon.
I'm hoping for what we have, which is a beautiful day to go up into the mountains.
Derek needs to sample the peak of this mountain because the rocks at the summit have been protected from relatively young volcanic rocks. Elsewhere, these younger rocks have intruded into old rocks, resetting their zircons and their geological clock.
Oh my God, I love this. Takes your breath away. We want to understand what's on top of that gosh darn heck mountain up there. We'll climb it if we got to get a piece, and then we'll bring it back and tear it apart in the lab and tell a story about it. Because again, that's, in the end, what we do is tell stories.
As they climb the mountain, so they traverse geologic time, walking over rocks that record successive chapters in the history of the ancient shield. Derek and his team gather evidence by sampling minerals from the bottom of the mountain to the top.
All right. Wow. I'm in heaven. Yeah. We're almost at the top. Almost at the top. We made it! By Jove, we made it! Holy jumping Jehoshaphat. There's even birds up here. We're barely out of breath, basically. Beautiful, 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 beautiful. All right, what's coming in from rain? All right, well, maybe it'll just pass through.
It's mission accomplished for the team from Memorial University. The trawler can now head for home, carrying its precious zircon samples for later analysis in the lab.
Now, down at the bottom of this sea right now, we might have a little sediment being deposited from the mountains back there, and maybe 2 billion years from now, they'll be up on land in a mountain somewhere. The Ramagoop will be gone, the Archean will be gone, it'll be all weathered away, out in the ocean. But I don't think there's going to be geologists 2 billion years from now.
All the way to the other extremity of the shield, the quest to find the oldest rocks in the history of our planet is also a passion for geologists. In the Northwest Territories, rocks dating back 4 billion years have been found. Throughout his research, Derek Wilton hopes to establish that the eastern part of the shield is also very ancient, perhaps even older than the western side. At the Zircon Dating Laboratory at Memorial, Derek will finally know if the Torngat expedition has been a success. He's about to analyze the first of the crystals and unlock their age.
Samples are all ready?
All imaged and polished and
They
ready
look
to go.
like good, and the machine is nicely finely tuned today. You know what's really exciting now? We were up in northern Labrador, climbing the mountains, had a great time, beautiful scenery and stuff like this, collecting those samples. We've brought them back, we've disaggregated the rocks, we've concentrated the zircons, and within 5 or 10 minutes on this machine, we're going to be able to analyze them and perhaps get an age date. And we might actually have some of the oldest zircons on the planet in those particular rocks that we gathered. So we're going back to the beginning of time. It's kind of really neat when you think about it. Based on these little tiny crystals right here. This is exactly what's going on in the laser ablation cell inside in there. The laser is hitting a crystal, and this is a crystal of zircon right here, piece of zircon, and it's drilling essentially a hole through that crystal. But by drilling through here, it's actually blasting the material out from the inside. The way the system works, of course, is a gas is flowing through here, and it transports most of this material to the ICP-MS, where it's analyzed.
Their age can be calculated from precisely measured amounts of uranium and lead.
The interior part was 3.3 billion years old, and the rim, these parts out here, were actually 2.8 billion years.
The zircons collected in the Torngats have allowed Derek to establish that the earliest mountains formed 3.9 billion years ago. By dating the different layers in a single crystal, he has also found evidence of at least 2 mountain building events over a time period of about 500 million years. The team from Memorial University has unlocked the secrets of the Torngats. Once thought to be so complex, its geology could never be fully understood. It is now realized that the shield was assembled over the course of billions of years by the same plate tectonic processes that are at work today. The lesson from the Canadian Shield is that plate tectonic processes of ocean widening and closure, of mountain building and decay, began very soon after the formation of planet Earth 4.5 billion years ago. The long building process that assembled the shield resulted in the formation of many successive mountain chains, such as those in the Abitibi region near Hudson Bay. Here the hunt for precious minerals is driven not by utility, but by the riches that come from the most sought-after prize of the Americas, the lust for gold. Geologist Michel Gauthier is trying to understand the link between the ancient mountains that once covered this land and the fabulous resources that lie underground. Michel and his colleague, Jean-François Ouellet, are hunting for clues that tell of gold.
Jean-François, ça a l'air pas pire là-bas. Il y a beaucoup moins de moi.
The discovery of highly deformed rocks is a signpost to the base of the old mountain chain. These beautifully banded formations called gneiss are shaped by hot plastic rock being squeezed as one tectonic plate rams into another.
Oh, this rock has suffered. Check out this fold. You see, Jean-François, this layer here zigzags back and forth, like an accordion. A deformation like this can't happen to surface rock. For rock to react like this, it has to be heated to extreme temperatures. It had to have been as soft as toothpaste.
These outcrops confirm that we are at the heart of the mountains, where the temperature was extreme and the pressure so great that rocks were compressed by forces strong enough to build mountains 2.7 billion years ago.
This rock tells us where the melting pot is, so our goal can't be far away.
Our geologists have found the crucible, where the rock was intensely heated by the crush of tectonic plates. The heat was so extreme that it dehydrated rocks of the mountain's roots, forcing hot fluids upwards into the body of the mountain, just as water steams from a burning log. Mineralized waters move dissolved gold higher up into the body of the mountain, a process that goes on for millions of years as the mountains grow. Working out from the mountain's roots, the geologists looked for the pathways taken by ancient gold-bearing waters deep underground. These pathways are highly complex, having been altered by later heat, pressure, and erosion. Their discovery requires painstaking examination of the ground for clues. Michel and JF systematically explore the area around the base of the ancient mountain. The treasure hunt is on. A few kilometers further away, Michel spots a clue. He's found the rocks that reveal the plumbing through which the gold-bearing fluids rose up through the mountain.
All of this, the white stuff, once looked just like these green patches here. This material has been entirely washed out. Lots of water went through the system. It's as if the rock was rotten, like wood that rots from exposure to water. The fluids that rotted this rock were probably carrying gold. We are definitely getting closer.
The ultimate clue is the discovery of a vein of white quartz, indicating the nearby presence of gold.
The gold-carrying fluids contain a lot of dissolved silica. When all of that solidifies in the faults, some gold will mineralize, but mainly you get crystallized silica, commonly called quartz. Smells like gold. We just collected some samples, and happily, we found copper. You can see the characteristic verdigris color, just like old copper roofs. Now that we found this, we know that we are almost there.
On the Canadian Shield, the presence of copper is almost always linked to gold.
There's gold in the system. We're at the right level in the mountain chain, and there's the plumbing evidence. The presence of quartz proves that lots of water flowed through these rocks. This is definitely the location to concentrate on over the next few months. It's major.
Searching for gold has its rewards. One site, explored by Michel and Jean-Francois, a few kilometers from the large quartz vein, revealed a valuable gold deposit called Eleanor.
This research is a passion and lots of fun, but it goes far beyond that. The discovery of Eleanor, worth billions of dollars, will create 400 jobs over a 25-year period. That's 400 people who'll have work in remote parts of Canada, where it's most needed.
It's a curious list. Gold, tools, weaponry, a dazzling array of other precious metals that can be mined and used to fuel the modern world. Its age and history have made the Canadian Shield a gigantic mineral storeroom whose wealth comes from below and above, even from outer space.
Look at this. I go anywhere I want now and trade. E-Trade Mobile Pro. Right on my BlackBerry. Hang on a sec. Hey girl, can I hit you back?
New E-Trade.
Over its 4 billion-year history, the Shield has often received some less than welcome guests from other worlds. Fiery meteorites pockmark the Shield's surface and threaten apocalyptic destruction, but have also brought unexpected gifts in the form of minerals. These large-scale impacts may also have played a crucial role in the history of life on Earth. Many scientists think that by eliminating the dinosaurs 65 million years ago, a large meteorite created new niches for life, such as mammals, and eventually ourselves. A similar meteorite struck the Canadian Shield near Sudbury, Ontario, 1.8 billion years ago, forming the huge Sudbury Basin. This is where geologist John Spray will take his daughter Laura to ground zero of the meteorite impact basin.
What's so special about this area?
Well, this area in particular shows a very unusual rock. It's called Sudbury Breccia, and I want to show you a beautiful example of it.
just down here. This is an unusual rock type. We don't get to see this type of material very commonly. The size of this is just amazing. So what we think is happening is when the meteorite came in, they hit the Archean shield and fragmented it. So these blocks here are like jigsaw pieces that have been smashed into fragments. Originally this was liquid, and you need a tremendous amount of force to generate enough energy to blast rocks apart like this and then melt them in between. So we can use this rock type as evidence for a very intense high energy event hitting or affecting the Earth. When that hits the planet, there's a tremendous release of energy, many times more than all our nuclear weapons put together released in one event. You have to try and put yourself back in that time period. You have to go back and imagine what it was like inside the Earth, perhaps, maybe 10, 20 kilometers below the surface.
John and Laura are on a journey 2,000 feet beneath the surface of the Canadian Shield. Into the depths of Sudbury's great nickel-copper mines. The Sudbury Basin produces hundreds of thousands of tons of nickel and copper every year, the biggest concentration of mines in the world. Ironically, this wealth was discovered accidentally by railway engineers constructing the Canadian Pacific Railway in 1885.
So what I'm looking for now, Laura, is some of the ore, which is sort of gold-colored and really stands out. And here we have, look at this, an excellent example here. This dark rock here on the side, the bottom of the impact melt sheet. So this material came down, sunk out as a dense liquid to the bottom of the impact melt sheet, and the ore then came through that because it's even heavier and it penetrated through this rock type. And this is what the miners are extracting here.
The force of the impact punched a hole through the Earth's crust, allowing the mantle below to well up and fill the basin with a thick sheet of melted rock. A tremendous shock wave shattered the surrounding rocks, riddling them with faults and fissures. Nickel-bearing minerals accumulated at the base of the melt sheet and were then propelled into the basin's fractured surface, only to be buried under huge masses of pulverized rock. The Sudbury underworld has been so minutely explored by drilling and mining that geologists are able to create computer-generated three-dimensional maps of the ore deposits. But what about the other impact craters of the Canadian Shield? Could other meteorites generate the same kind of industrial wealth? Geologists identified at least 50 meteorite impact craters on the Shield surface. Further exploration of some of these sites could yield informative results. John and Laura will now travel to a remote impact structure at Manicouagan, deep in the wilderness of northern Quebec. To this date, scientists know very little about its history and its mineral potential. René-Levasseur Island is the result of a large meteorite that struck here 213 million years ago. Could there be ore deposits here, just like the ones of Sudbury? There is much less known about Manicouagan, no mines and no 3D models. The research will take decades, but the stakes are very high. Our explorers land at a mining exploration camp on the island. The only way in or out is by float plane.
Nice to meet you. This is Laura? Hi, Laura. A little different from Sudbury.
Upon arrival, John and Laura meet Constantine Salamis, the founder of Manicouagan Minerals.
What you're looking at here is a number of semi-permanent residences This is our kitchen.
Like other adventurers before him, Constantine has dreamt of finding nickel deposits in Manicouagan for nearly 20 years.
Yes, and this beautiful core.
Millions of dollars have been spent drilling up to 1.6 kilometers deep. Despite intense research and drilling, the Manicouagan crust has not yet revealed its secrets. Constantine is running out of time and money. He needs the expertise that John can provide, but it could prove difficult. Manicouagan is much younger than Sudbury, a mere youngster of an impact crater, only some 300 million years old. If ore is present, it will be much deeper, since the young crater has suffered much less erosion compared to the 1.8 billion year old Sudbury Basin. Undeterred, John will now push his exploration towards a smaller island not yet explored by geologists. It is there that John will look for evidence of a melt sheet and the potential treasures it might hold.
Now what we have to do is look at our geological maps, move around the island and try and find exposures where that contact between the melt sheet and the footwall can be seen, and we can walk around and sample it.
John's instinct has led him to one of the most relevant rock structures of the whole crater.
This is a great place. We're right at the contact between the bottom of the melt sheet and the basement, Precambrian basement rocks underneath. And here at Manicouagan, this is special because we don't generally see the contact very well exposed. We had a very similar rock to this at Sudbury, and it's this type of rock which contains the ore at Sudbury. And so if you were going to explore for metals here in Manicouagan, the very place you'd look is right here, because we're right underneath the melt sheet.
John's discovery justifies more sampling over the next few days, but time is short. Long-term research is needed that could provide answers from the many cores from previous drillings. The cores serve as a time capsule that allows scientists to reconstruct the deep structure of the crater and to unravel the mysteries of how it formed.
What we'd like to do with the core is specifically to have Catherine look at the impact melt sheet to take samples every 10 meters. So you'll be prepared to let the university take this material and store it safely in a secure place. That would be fantastic.
It would be wonderful.
Yeah. Well, we've got millions of dollars of material here.
Exactly. Which
is an amazing scientific asset which many people can work on for decades into the future. So if we have these very comprehensive drill core sections, we can then start to rebuild these stratigraphic sections through the structures themselves.
Our geologic journey across the Canadian Shield ends at its very beginning in the far western extremity of the Northwest Territories, among the oldest known rocks in the world. These are part of the Slave Craton, where geologic time began, the very place where the North American continent was conceived. The Craton records 3 billion years of tectonic history. Largely completed 1 billion years ago, it has since undergone deep weathering and stripping, glaciers taken away and giving. In the course of the marked climate swings of the last 2 million years, ice sheets have come and gone, sculpting the shield and cutting large valleys and thousands of lakes, great and small. It may seem inhospitable, but this landscape was kind to the pioneers who pushed their luck north of Yellowknife. As elsewhere, they were lured by gold,
There was a quartz vein with enough gold in it that they mined it at one time.
Prospector Walter Humphreys is among the last of these low-tech adventurers who traveled not by helicopter, but by canoe and on foot. He's one of the old school who explored by observation on the ground, and he's looking this time for diamonds. But where did they come from?
The chance of a prospector finding a mine in his lifetime is pretty remote. So most of us realize we're not going to find mines. We might find showings, but the Territories is a big country. There's still a lot of possibility up here. Tomorrow I could go out and find some indicator minerals that could lead to a diamond mine. That part is very exciting.
Geologists speculate that about 2 billion years ago, the destruction of oceanic crust drove carbon deep into the mantle, where diamonds formed under extreme heat and pressure. It's believed that jets of molten rock form narrow pipes called kimberlite. This is the conduit by which diamonds can be thrust to the surface. It is these pipes that Walter is searching for, but his quest would be impossible if it hadn't been for Ice Age glaciers. Thousands of years ago, huge sheets of ice covered the entire shield. By scraping the rocks below and removing the top of kimberlites, glaciers carried and dispersed diamonds and other minerals. By sampling glacial sediments for characteristic minerals, geologists can identify the presence of a nearby kimberlite pipe. Walter is looking for some of these signs. He may have found something on an assessment report filed by a previous explorer of the region.
Well, these little circles are little circular anomalies, so that might indicate a kimberlite. So I think I'll stake it up to see, and then do some sampling on it to see if it is a kimberlite.
Walter's search may yet prove fruitless, but elsewhere, kimberlite pipes are being mined for their high-quality diamonds, gifts from the mantle to the Canadian Shield. A laboratory for the study of deep time. The refuge of dreamers. A magnet for adventurers. A home for North America's first peoples. The Shield has captured the imagination of scientists, travelers, poets, and artists. A landscape that repels and attracts, where weather and terrain are the masters of the universe. The Canadian Shield is one of the last frontiers of the exploration of our planet. There is still much to be learned about what lies hidden within.